Hello everyone, my name is Vinicius Mattoso and I'll present the work developed by me, Dr. Damamaza, and Professor Isabelada and Márcio Carvalho. This work is called the Reservoir Characterization using the ES-MDA method combining pressure and temperature data. This work is a part of my master thesis. Here is a summary of this presentation, which starts with the contextualization of the problem, followed by the goals of this work, the problem that we are trying to solve, the Well-Resrvoir simulator, and the ES-MDA method, and finally we present the results. This work is inside of the management area and more specific into the reservoir characterization. In a summary way, a reservoir characterization means to estimate the reservoir properties such as different permeability values and regions. To make the characterization of the reservoir is necessarily some data, and to obtain this data, the well tests are commonly made. This test consists in the controlling process of open the production valve during the drawdown, followed by a static period called the build-up. During the whole test, the pressure and temperature data are registered. Despite having both data available with good resolution, commonly only pressure data are used to make the reservoir characterization. The main goal of this work is to characterize the reservoir using the ES-MDA method considering pressure and temperature data. To achieve this work, we perform the analysis of the CD matrix from the ES-MDA, that is the covariance matrix of the measurement error, and evaluate the gain of using the coupled data. The problem consists to estimate the permeability from the reservoir based on the data. For this, we simulate data with non-permeability values and use the optimization method to make the history match, and then we estimate the values from the permeability. In order to estimate a range of values as response, we use an ensemble of simulated models and make the history matching using ensemble-based method to obtain a range of value as response for each parameter. To build the set of the simulated data, a non-isothermal well-reservoir simulator developed by LMMP from PUC-Rio was used. The simulator was developed in MATLAB using the finite difference method, and it consists of a well-bore coupled with a 1D cylindrical reservoir running under the single-phase flow. The observed data was captured from the sand phase, that is the connection between the well-bore and the reservoir. And to simulate the measurement data, a normal distribution noise was added into the simulated data. The ensemble smoother with multiple data simulation is an ensemble method that makes interactively global updates in the vector of parameters M and have this update formula, where CMD and CDD is created in this way. The alpha E is an inflection factor that obeys this rule. The CD, as mentioned before, is the covariance matrix of observed data measurement error. The Duke is the observed data, and D is the simulated data. The reservoir analysis has a skin zone with a lower permeability near the well, followed by a homogeneous zone until the end of the reservoir. Analyzing the log-log derivative plots, we can observe that the pressure has only a single plateau, which indicates that the pressure is seen in a reservoir with only one permeability zone, and the temperature derivative plot to have two plateaus, which indicate that for the temperature we are seeing a reservoir with two permeability zones. The ES-MDA were performed during 4 simulations considering an ensemble size of 100, and the inflection factor was set constant and equal to 4. The log scale was used to reduce the amplitude of the permeability and gave this Gaussian format that required from the method. To create the initial distribution was used a normal distribution with mean 5 and a standard deviation 1 for both logo permeability and for the alpha skin. Alpha skin is a variable that makes the correlation between the radial of the skin zone and the radial from the well bore. And for the porosity, was also used a normal distribution with mean 0.2 and a standard deviation of 0.05. Two configurations of the CD matrix were analyzed. The first one was used the reference value used by Silva for pressure data and the values used from Wohan 2 for temperature data. Due to the magnitude of the pressure and temperature data is much difference, both the matrix, CD matrix and observed data were normalized by the initial values. The other CD matrix configuration were created based on the SWE PAD thesis, in which was used the Joule-Thomson coefficient to make the correlation between the pressure and temperature data for the Levenberg-Marquardt method. Additional weights and considering the CD matrix equal to identity matrix was also evaluated. Now, the first result from the CD matrix analysis is that if you consider the CD matrix as an identity, it didn't make much regularization, and this result repeats for all variables that you are looking for. And making a zoom in the other configuration, we observed that all of them achieves accurate estimation due to the initial distribution of the skin permeability was from 7 millidarcy to 1.1 darcy. And the configuration with both configurations with the addition of weight of 10 power less 4 achieve the most accurate estimations. So, to evaluate the use of the coupled data, we compare the estimation for each parameter, considering only pressure data and the coupled data for both configurations. And as expected, the single pressure data was not sufficient to make the estimation from the skin permeability zone, while the coupled data estimated with a good accuracy this permeability zone. And for the homogeneous permeability, the use of the pressure data achieves a good estimation, but using the coupled data, we make estimation with less than 10% of error. As expected one more time, the only pressure data is not sufficient to estimate the alpha skin, and using the coupled data, we are able to make this estimation. And for the porosity, the use of the coupled data also made estimation better than considering only pressure data. Here, the data matching between the observed data in red and the last simulated data in blue. In gray, we have the simulation for the initial distribution for only pressure knowledge. Although the data matching is near to the expected, some parameters of the vector of parameter were estimated incorrect. Here is the data matching for the coupled data using the first CD matrix configuration with the addition of the 10 power less 4. The matching was accurate and the vector of parameter achieved values close to the expected. And here is the data matching for the coupled data using the second CD matrix configuration with the addition of the 10 power less 4. In this configuration, the data matching and the parameter estimation achieve the most accurate results. So, as conclusion of this work, we successfully applied the ES-MDA method. Using of coupled pressure and temperature data can be used to estimate the reservoir parameters. The addition of the temperature data improves the near well and porosity characterization, and the CD matrix equal to identity and Joule-Thomson coefficient with the 10 power less 4 additional weight present the most accurate results. Finally, I'd like to say thank everyone for the attention and thank you for this institution for the financial supports.